Okay, so let's talk about what we did last class and get on to topics for this class. So I asked last class, what was quality? What is quality? And then I gave you a statement, the degree to which the product conforms to an engineering design specification. And we decided to brainstorm as a group to come up with some attributes that help define what we're looking for in quality. And these came out as we discussed these well filtered, and we were discussing water at the time. How do you define quality of water? If it's a chemical process, it's defined as how many parts per million of certain chemicals have been added to purify the water. If it's someone like number 4 where it's taste, that's going to be a little harder to define, but that's how you wind up doing things for breweries, whiskey companies. They have master taste testers, and they know what they're trying to taste for. So it's a little harder to deal with, but it's a well filtered is a attribute. So I have no qualms about that. Someone mentioned good craftsmanship. That's one of the major categories of quality. How well were things made? Were the people that assembled it craftspeople, or were they just really shoddy? We'll need to come up with some definitions of units or some way to measure that, but we can find that. Okay. Number 3 was consistency, and we talked about size, color, etc. That's pretty easy to define. We're looking for a black that is called Parson black, for instance. We might be looking for a blue that's navy blue. We might be looking at an orange that's pumpkin orange. We can come up with a color chip to define what that color is. Size, it's all down to measurements. So that would be something measured in inches. Okay. And then number 5, we talked about durable. And that would be like shear stress, impact testing, things hitting other objects and not breaking. We can put that in some engineering terms of shear stress. I'm just going to leave that one as shear stress for now. 6 is how strong it is. We have a tensile strength on things. We have compressive strengths on things. We got a concrete bridge that's supposed to have 6,000 pounds per square inch of concrete in it. Well, that's the measure we can actually test. Okay. And then number 7 is reliability. Reliability is a lot of sub-attributes, but let's just play with this one for time. Does the object we're using have a longevity in time that satisfies the expectations of the specifications that were requested for by the people looking for that product? Okay, if you were trying to buy a hammer for framing, you'd want a hammer that's going to last years and not one that lasts half a job and the head starts chipping and that sort of stuff. Okay, so that's what we're looking at. So generally, this comes down to this next statement. Okay, so the extent to which the end user feels that the product performed its function, and it can be of a nature that it, well, we could define it as met the function. It could have surpassed expectations. Okay, so maybe I'll make that as a met or surpassed expectations. Okay, it could also believe that it didn't meet the expectations, so that would be a downside on that. Okay. All right. So that's some basic rules. I'm going to talk about how do we inspect for quality. So um, so in inspecting for quality, we got to come up with a way to measure things. We'll talk about measuring and what we got to do for different things down the road. But right now, let's just talk about how do we inspect for it. Well, one of the ways is, let's write this down as ways to inspect. Okay. And what we're going to find is that there is the old standard. Oh, that really didn't work out right. A 100% inspection. And you'll have to try to achieve accuracy on 100% of it. So it's, come on, you got to go away. Stop doing that to me. Get out of there. Okay. 100% inspection is more about looking at measuring %100 of the items. Okay. That's not really doable, and I'm going to run an experiment for you later, and it's called Find the F's, and you will have to count the number of F's in a paragraph and see how many times you come up with the same number and how everybody else does it. So, all right, so 100% inspection with one person. One person, not people, one person would / could have error. Okay. What about if we did it with 4 people? The number of errors will be reduced, but not eliminated. Okay, so by this I mean when the first person could be looking at things and they may do their best to find things, but if you give them 1,000 parts to look at and you give them a short time frame to do it, eventually they're going to get burned out of looking at the particular parts and pieces you're trying to find. So that's not going to help them in the long run. If you bring in more people, so let's put in 4 this time to inspect these, you're going to force them to do, the first person looks at it, the second person looks at it, and by the time we get to the third person, we are literally finding more errors and getting them caught, but we're costing a lot of money in this process. So adding more people isn't always the better solution. Okay, so think of it that way. All right, so and the best way to do this, though, is what we get into, and we're going to start with this topic, is statistical process control. So we're literally going to sample things and use statistics to help us prove how well we're doing. Okay, so let's set up these scenarios here. We got an acceptance test. Okay, and we're going to look at a process for this, and we're going to figure out where we are actually going to be able to test. So let's do this. I'm going to draw, here's a process of making something, here's another process, here's this process, and then we're going over to this process, and we got these. Okay, so let's just call this A, B, C, D, E. Okay, so we start things going in. B has something coming in. Both these go to C. Sometimes we may have to take a look at A going to B, and then C to D, and C to E, but then E could go to D, and then when we're done, we're kicking out of here, and we're on the inside and outside of a box like so. And where are we going to inspect? So we can inspect, and I'm going to use I for an inspection. No, I can't use that. We got Roman numeral I there. I'll write it out. Inspect on the way in, and we can inspect on the way out. Okay, but we had processes inside this operation that defined what the quality was going to be if you missed it. And by the way, let's put a N here of 1,000 pieces that are going to go through this process. So when we get all done, we literally have a chance that 1 in 1,000 are bad, 10 in 1,000 are bad, 100 in 1,000 are bad, or literally all 1,000 are bad. Okay, so having inspection on the inside and inspection on the outside doesn't really help us. But we could inspect in here at these stages between the parts, and then we can have a final inspection out here. Okay, so there are ways to narrow down and reduce the total error in the system, but we have to put more inspectors in place. Okay, so it means more people trying to see things. Okay, the day of getting more computers to do things, we could have more things that'll do that. Okay. So I want to do this, okay? So why do we want an acceptance sampling? And why do we do it? Well, it's need a point to measure the value of the product. Okay, so if I only measure the value on the outside, the output side, I guess I should put that up there as output, then the whole point is anything that happens inside the little black box is not going to get measured. So I can't find, well, this is why not to inspect on the outside. So let me rephrase that. So why we do it is we need a point to measure this. Improvement of inspection would get the root cause of the error. And I'll explain this in a minute here. Okay, so the more points that I put in, like, I guess I should use a box, in here inside the process, that's the more data I'm going to have on what was the cause of the error. Okay, so we're going to look for the root cause, but in order to do that, we have to measure more. We can't just rely on leaving things to a chance. Okay. If we only inspect out at the output, only measure at the output, we okay, so if we only measure at the output, only measuring, yeah, I guess I better fix that. Only measuring output, we don't know the cause of the error. Okay, and this whole process is always looking for cause and effect. And I will take you into what's called an Ishikawa diagram later in the semester, which helps define where the error is going to be and how you actually make improvements to things. Okay? So, and if we do it only at the output, then it's too late to actually make any continuous improvements and improve the product before it leaves the factory or leaves the job site or whatever we're doing. Okay, so we want to fix that, but we need to do it by measuring more at individual places along the way. Okay, and I think that's where we'll kind of stop this little lecture, because I want to keep these short. I don't want to make these too long, and I'll add another one in tomorrow, and I'll fill in some more details on this. Okay, keep your eye out for the little video series here to make up for the lecture that we missed today.